In signal processing, a filter is a system that operates on a signal to reduce or enhance certain properties. Digital filters are widely used in multimedia, biomedical engineering, electronics, communications, and many other areas. In this video, we will see how you can design and analyze digital filters and apply it to a signal. I will provide answers to following two practical questions. How can I remove an unwanted tone from a signal? And how can I compensate for the delay introduced by a filter? Let me show you how you can remove an unwanted tone from a signal. A tone is a signal that rings only at one frequency. Let us load a signal into MATLAB. The signal is a series of voltage readings corrupted by noise. Often it is hard to tell anything about the nature of the noise just by looking at the signal as a function of time. We can visualize the power of the signal across different frequencies by using the function periodogram. You can see a peak around 60 Hz in a plot. This peak is likely caused due to the presence of 60 Hz power lines interference, which corrupts electrical signal measurements. We can use a bandstop filter to remove the 60 Hz interference. A bandstop filter with a narrow stop band eliminates a tone of particular frequency. We can use the design-field function to design the bandstop filter. We specify the stop band to be in the 59 to 61 Hz range. We can analyze the filter response using the fvtool command. The next step is to filter the data using the filter command. Let us plot the power spectral density of the filtered signal. We can clearly see that the bandstop filter has removed the 60 Hz noise. In this way, you can use a filter to remove an unwanted tone. We just saw how to use a filter to remove an unwanted tone from a signal. The filtering process, however, also affects the signal by shifting the output in time with respect to the input. This delay is a consequence of the filtering process, and we need to compensate for the delay before processing the signal further. I will now show you how to do that. Finite impulse response or FIR filters introduce delays that are constant over all frequencies. On the other hand, the delays caused by infinite impulse response or IIR filters vary with respect to frequency. Now let us take a look at how to compensate for constant filter delay. Let us load two signals. The blue line represents the original signal, while the smooth red line shows the result of passing the original signal through a low-pass FIR filter. The process removed sharp variations in the original signal, but clearly introduced a delay that time-shifted the output with respect to the input. The group delay function allows us to determine the nature of the delay introduced by the filter. In this case, we see that the delay is constant, independent of frequency, and has a value of 35. Knowing this, all we have to do to align the original and the filtered signals is shift the filtered signal by 35 samples. We can verify the result by plotting the original and the delay compensated filtered output on the same plot. Now we will see how to compensate for frequency dependent delay. Here is an original ECG signal in blue, and the red line shows the original signal filtered using low-pass IIR filter. Recall that filtering introduces a delay. Let us determine the nature of the delay introduced by the filter using the function group delay. This plot shows how the delay varies with respect to frequency. To compensate for the frequency dependent delay, you can use the function filtFilt. FiltFilt performs zero-phase digital filtering by processing the input signal in the forward and the backward directions. Using filtFilt, you can compensate for frequency-dependent delay and filter the signal. To summarize, in this video we have seen how to remove an unwanted tone from a signal and how to compensate for the delay introduced by a filter. To learn more about digital filtering, please refer to a practical introduction to digital filtering example in the Signal Processing Toolbox documentation.